The other type of distribution that we look at that's a continuous distribution is the normal distribution. But before we get into there, we're going to see a little bit of a change in our notation. When we first started out, we just started describing the sample mean and the sample standard deviation. We'd use the x with a line over the top of it to represent about the sample mean, the mean of a sample, and S is the standard deviation, sample standard deviation. Here in this section, we're going to be start talking using these two symbols. We're going to be using mu, which is this sort of fancy U-shaped graph, U with a little extra foot on it, pronounced mu, and spelled as mu. But that represents the population mean. And then sigma is like the O. I like to call it the O with the comb over. It's got that little piece of hair that it's trying to cover its bald spot with there. It's the population standard deviation, and it's pronounced sigma, and it's actually spelled SIGMA. So we're looking about the distribution of a population. So a lot of this time we'll be using mu and sigma. All right, so besides the uniform distribution, the other distribution that we use a lot is the normal distribution. And by normal distribution, that really means the usual distribution. It turns out that when we start looking uh, at graphs of distributions of things that occurred in nature, we'd have this distribution that would show up over and over and over again. It's a nice bell-shaped. Boy, my drawing's not coming out so well. Let's try that again. Try to do it nice and smooth here. It's a nice bell-shaped distribution that is nice and symmetric. There we go, a little bit better in there. The peak here in the middle is where your mean of your distribution would be. It's whatever that middle is. And the standard deviation, there's a point here on our curve where it changes from being concave down to being concave up. When it changes from being concave down to concave up, it's nice and symmetrical. It's the same distance on either side of mu. And it turns out that that distance is the standard deviation. So that standard deviation shows up as a nice physical distance here on our graph as the distance from the mean out to those inflection points in there, where it changes from concave down to concave up. So it kind of tails off to both the left and the right. It's nice and symmetric, but to the point where it changes from being an umbrella shape to being, I don't know, a slope shape. And I guess it's all kind of a slope, but that is your standard deviation in there. That inflection point where you change concavity is that inflection point. It turns out that a lot of times that for these normal distributions, we have a handful of percentages that are associated with them. If you go one standard deviation on either side of the mean, you capture 68% of the data, 68% of the values, whatever it is that you're looking at, the measurements are within one standard deviation of the mean. So this interval where you go over an interval to the left and over an interval to the right from that center, from that mean, you will capture 68, about 68% of the population. If you go two standard deviations, you get 98% of the values. Are within two standard deviations, within two sigmas up there. So if I take that sigma distance and I repeat it over again, I take that same distance and double it kind of out each direction, we end up with 95% of our values end up within that range of values in there. And if you go to three standard deviations, you get 99.7% of the values. are within 3 standard deviations. So almost everybody is within 3 standard deviations. There's a small percentage that's not. So if you go 3 standard deviations in there, so it's a specific rule that holds for normal distributions. Other distributions, like the uniform distribution, it doesn't happen here. So this normal distribution, again, if you're looking at that, you're likely to get values close to the mean here. That's why the graph goes up in there, and then it tails off. That as you go farther and farther away from the mean, you're going to go that. Suppose that it takes a popcorn, for an example. Suppose it takes a popcorn kernel to pop is normally distributed with a mean of 50 seconds and a standard deviation of 5 seconds. What that would mean with the empirical rule, so, well, maybe let's draw a graph of our distribution. Here's our distribution, our normal nice symmetric curve, bell-shaped curve there. So in the middle of that would be the 50 seconds. Right at that highest peak is going to be our 50 seconds. And then it looks like my inflection point is roughly right about here in the way I've drawn that graph. And so at this lower inflection point, the scale on the x-axis would be 45 and it would be 55 on the other one. I'm going 1 standard deviation on either side of the mean so that I know that 68% of kernels pop uh, between that 45-second mark and the 50-second mark. Oh, no, 55-second mark. Sorry, I did that wrong. Got to add that standard deviation to both sides, that 55-second mark in there. And then if I go another 5 seconds, so repeat that distance over again, if I'm going to, let's see, that would be 40 seconds and 60 seconds, and I'd get 95% of the kernels popping. There between that 40-second mark and that 60-second mark in there. So you got a nice continuous distribution in there. And we get a lot of them, instead of being, if it was a uniform, it would be sort of at any instant, anyone could possibly uh, park pop at any time. But on this normal distribution, you're more likely to get pops right around that 50-second mark in there. So you're getting more of it in there. You've gone over the same amount on a uniform distribution, the percentage would stay the same in each one of these 5-second intervals, but it doesn't happen on the normal distribution. You're more likely to get something within that those two intervals. And if you want 99.7% pop between one more standard deviation. So that would be 35 seconds to 65 seconds. We're going to get 95% of those kernels to pop. 99.7% of those kernels will pop between 35 seconds and 65 seconds in there. Of course, it depends on the microwave, but we're going to assume that we're looking at a particular microwave here or something like that. Another example we might have would be adult heads have a circumference that's normally distributed with a mean of 68 or 48 centimeters and a standard deviation of 13 centimeters. So if we can get our knit hats to expand to 48 minus 1.3 would be 46.7 centimeters to 48 plus the 1.3, 49.3 centimeters. So if we can get our hats to go from 46.6 centimeters to 69.3 centimeters, that'll fit 68% of adults. So if we have a kind of stretchy knit hat, it will do that. If I can do another 1.3 centimeters on either side of that, I should be able to get 95% of adults. That if I can go from, let's see, it'd be 45.4 centimeters to 50.6 centimeters, then I'm going to be able to fit 95% of adults. If I get enough stretch in my hats to do that, I can get a whole bunch of my population would be able to wear my hat. If we go one more, if I go to 44.1 centimeters to 51.9 centimeters, then I should get 99.7% of our population. So I don't know at what point we can call it one size fits all, but it doesn't quite fit all. But if I can get it to stretch from 44.1 centimeters to 51.9 centimeters, if I can get that much stretch in my hats, I will fit nearly everybody in there. All right, so that's kind of nice with these special values, and that's what you'll find in 6.2. We don't have any homework problems on 6.2, but it kind of gives us this introduction of what the normal distribution is and how it's shaped, and this 68, 95, 99.7 rule could give us some nice approximations in there to get a value there. Um, when we want to get a little bit more serious about normal distributions, a lot of times we'll want to use this z-score in there. And it might be a way to standardize your distribution. It's a way to convert from any normal distribution to the standard normal distribution. The standard normal distribution is a specific distribution. You've got a normal distribution that describes things with all sorts of different means and standard deviations, but the standard normal distribution has a mean of 0 and a standard deviation of 1. And the way that you can do that if you're trying to find like an area underneath the normal distribution is we convert to the standard normal distribution with a z-score. And you take your observation, so whatever observation you're looking at, we want to look at sort of how far away from the mean is it each point observation minus the mean and divide it by the standard deviation. And that will tell us sort of how far a relative distance from the distribution in there. So for example, if I have two different microwaves and one microwaves pops it with an average time of 45 seconds and a standard deviation of 4 seconds, and we have a different microwave that pops kernels a little bit faster. It takes 66 seconds to do it, and the standard deviation is 3 seconds in there. Both of these we're assuming are normal distributions. Um, and we want to know if we put a bag of popcorn in for 80 seconds in the first one and 70 seconds in the second one, which one bag will have more popcorn kernels. And a nice way to do that is to look at the z-score. So if I look at the z-score for the first one, I'm going to run it for 80 seconds. And I know that the mean is 75 and the standard deviation is 4 seconds. So that's going to give me uh, 5 divided by 4. I'm looking at 1.25. So that means this 80-second value is 1.25 standard deviations above the mean. You're kind of looking at a relative placement on your distribution. Are you 1 standard deviation, 2 standard deviations, 1.25 standard deviations above the mean in there? Our second one, we're going to run for 70 seconds because its mean is only 66 seconds and the standard deviation is 3. So that's a difference of 4/3, 4 seconds, divided by the 3 seconds. So it'd be 1.33 standard deviations above the mean. So we're running the second microwave a little bit longer relative to its distribution in there. So we should get more popcorn out of that uh, second um, second distribution there. All right, and then sometimes we want to look at uh, those values on our calculator, and there's a nice way to do that. There's a command called normal CDF, here that allows you to get to that. Let me hop over to the calculator and show you what that is. There is my smart view there. So what we want to do, it's under this distributions label. It's up above the variables one. So going to push the second button to access the blue command distribution, and I'm going to choose the variables VARS there. And the one we want to do is this normal CDF. We want to do the second option down there, normal CDF. Um, And this calculator gives you a little bit of a builder in there where you can put in your lower bound and your upper bound. And so if we're running that first calculator, I want to generally look from negative infinity up to that 70 seconds. So I want to go from negative 999 to 1.25 as my z-score. And I'm going to leave mean as 0 and the standard deviation of 1. What this tells me is that I should have like 89% of the kernels will pop uh, from that first microwave running for that 1.25 seconds in there. So it tells us the percentage of your population based on those values. And if I want to look at the second one, again, I'm going to go into variables, VARS, uh, and I'm going to choose this normal CDF. Lower bound was still negative 1.99, and I'm looking at 1.333. It was 4/3. Actually, I can just enter that in, I think, as 4/3 was my upper bound. Should be 1 1/3, 4/3 in there. Still, let's leave the mean at 0 and the standard deviation at 1 because we've calculated a z-score. We're looking at z-scores here. Um, Now, your calculator may not have that builder thing to it. It may jump right to the normal CDF with the parentheses showing up, and then you have to type in the 1.99 and the 4.3. You actually don't need the 1 and the 0 if your calculator's not automatically sort of taking you to this function builder. You can leave those out in there, and it will automatically assume that you're using 0 and 1 in there. So yours might start with this parenthesis here and then the negative 1.99. The comma, when you need it here, is right above the 7 is the comma to separate out those two things. I don't want commas now. It will give me an error in there. And so you can type in your expression for your normal CDF, and we'll get 90.8%. So that second microwave that we're looking at will pop about 91% of your kernels, whereas the first one will do 89% of your kernels. Hopefully that's enough popcorn for us either way around. But it can't go too long or it will burn the popcorn. So the stuff that popped earlier will already burn. Okay. Um, so back to this. Okay, so yep, so we're looking at the normal CDF is typically the command that we use in there, and we're doing it. So let's look at let's do the first microwave up there where um, the mean is 75 and the standard deviation of 4. So I want to do uh, normal with a mean of 75 and a standard deviation of 4. And so what I can look at is I can look at what percent of our population will will pop in that 80 seconds, and that's the probability that any given single kernel will pop in that 80 seconds. So I know our mean is 75, our standard deviation here is 4, and I'm looking at 80. What's the chance that in those 80 seconds I end up with a single kernel will pop? And so then I'm going to do that same sort of thing. You can do the normal CDF. We're going to calculate the z-score, take our observation minus the mean divided by our standard deviation. That's going to give us 5 over 4, which is 1.25. And then to find this area, I want to convert it on the standard normal distribution, normal CDF from negative infinity up to this 1.25. Again, I'm working with a mean of 0 and a standard deviation of 1 in there. And that should give us, well, I think we just calculated that. Should be the same sort of thing. It should give me the 89.4. So 89% of the, oops, wrong window. 89.4, 0.894. So 89.4% of the kernels will pop. So that one individual that I look at, it has an 89% of chance of it popping, right? So it's the same as the population proportion. The probability is the same as the population proportion. Does that make sense? So like if you had if you had a bag of M&Ms and you know that 20% of them were green, your probability that when you reach in and pull one out that you get a green one would be that 20%. It's going to be that same percentage in there. Okay. How about another example? We know that recovery time from an anesthesia is normally distributed with a mean of 20 minutes and a standard deviation of 4 minutes. I want to know what is the probability that a person recovers in 15 minutes. So we have a normal distribution, and the mean is 20. I always like to draw a picture just to kind of help me look at what I'm visualizing here. And I know the mean of standard deviation is 4, and we want to know what's the probability they're going to recover in under 15 minutes. So we want to know what's the probability I end up down here in this section where it's 15. So let's calculate a z-score. I'm going to take the 15 minus the 20 divided by the 4. It's the observation minus your mean divided by your standard deviation. So now I'm going to get a negative 5 over 4, a negative 1.25. And then I'm going to go to normal CDF. And I want to go from negative infinity up to negative 1.25. Again, you can stop there if you have to type it in yourself. But if you do that fancy building thing, you want it to be 0 and 1 for the mean and the standard deviation. So let's hop over to the calculator. And I'm going to go here into distribution. Again, second, get that second function of the variables right here, the second vars. And then I want that normal CDF. That's the one we're always going to use, is the normal CDF. You have to give it a left and a right and. Again, we're looking at that left-hand side, so we're going to go from negative infinity, and then our upper bound would be negative 1.25. And then I'm going to go and paste and hit the enter key to do that work. There we are. We're getting a 10.56 as our answer, 10.56%. So we're going to get 10.56 percent of people recover in uh, under the 15 minutes. Okay. And then if I'm looking at what's the probability that they take over 25 minutes to cover, I'm looking at this area up here. And so if I'm looking at the over 25, I'm going to calculate my z-score the same way. Uh, I want to do 25 minus 20 divided by 4. It turns out that's also still 1.25. And then so now I want to do the normal CDF. But I'm looking for this upper tail probability from 25 and above. And so I want to start my left-hand bound for that is 1.25. and I want to go to positive infinity up there. Just a bunch of nines, a really large number will work up there. So that should give me my probability there. Uh, I think it should turn out to be just because the distribution is nice and symmetric. I think this is going to come out give us the exact same number. Normal CDF, I want to do from 1.25 to a positive infinity. So I'm going to put in some nines there. Again, still mu 0 and sigma equal to 1. And it does give us the exact same value because I chose a nice and symmetric values. You're the same distance below the mean as you were above the mean. And so the probabilities worked out to be the same. But I had to enter it in the calculator different because, again, wrong slide there. Because I'm looking for that upper tail. And so it'd still be 10.56% of your population that will take over 25 minutes um, to recover. The next part that we want to look at is sometimes working backwards. Sometimes we're asked to work backwards. So maybe we want to find that time. Where's that time when, actually, I'm going to change this from 90%. Can I change that from 90%? Select. So is it going to let me edit that? I guess not. I'm just gonna manually edit. Let's just set a 90% because we've been doing right around 10% before. Let's go 80%. So I want to look at 80% of our parent our patients will recover after 80% of our customer service. So I'm trying to find what is this time down here. I know that the mean is 20 and the standard deviation was 5, 4. 4. Standard deviation was 4. And so the difference now here is I'm given the percentage and I want to work backwards. And we do that with the inverse norm. It was in that same spot that we saw the other one. I want to do inverse norm to get the z-score. And you have to give it the percentage of values to the left, and it will spit out the z-score that you're looking at for there. So I'm going to go to my calculator and do inverse norm. Second distribution, inverse norm. And we're going to do 0.8. We did 80%. So the area is 80%. Mean is 0, standard deviation of 1. Mine is fancy. It's giving me the option of whether I want the area, that 80% to be to the left of the mean, to whether it's to be to the right of the z-score I'm looking for, or whether I want it to be in the center 80% out there. Not all calculators have that left, right, center option, but some of them do. If you do, you got a little lucky. It works there. So some of them won't have that. If it doesn't have that, it always assumes left. If you don't have that left, right, center option, it's always going to assume left. So I want to put in the 80%, and it's giving me here a z-score of 0.841. So I know that the distance out there that I have to go is 0.841, and that's my z. But I know that z is the observation minus the mean divided by the standard deviation. Mean is 20, standard deviation is 4, and that gives me a little equation. I can do some algebra and solve for x. So multiply both sides by 4. Let's see, that's be 3.364 is equal to x minus 20, and then you add the 20 to both sides, and x is equal to 23.364 minutes. So it's going to take 23.3 minutes at the 23.33 minute mark after we stopped administering this anesthesia. We'd get 80% of our patients would recover after that value. Okay. And again, if we're looking at the uh, that we want the slowest 5% of patients. So the ones that we have to wait around for the most, where is that going to be? Where you're getting that 5% up here at the upper end? How long is it when I want to know, the patients that recover the slowest are going to be there for how long? How many more minutes above the 20 is that going to be? In this case, the areas to the right is 5% of whatever value. I'm trying to find this mystery spot there where the area to the right is 50%. If you don't have the calculator that has the left, right, center option, you always have to feed it the percentage that's on this side, that's on the left of the point that you're looking at. So if I'm looking at the top 5%, the longest 5% up here, I need to do 1 minus 0.05. I want to put 0.95 into my inverse norm of 0.95. You want to put 0.95 in there to get my z-score out. That's going to give us our z-score in there, 0.95. If you don't have that left, right, or center in here, if I have that left, right, and center, I can just choose right. But again, a lot of times we don't have that option. So I want to do 0.95 in there. And we're going to stay to the left, 95% to the left, because I'm going to stick with that because that's what the default is on some calculators. And so you might get lucky and have a calculator that's got a little bit more advanced operating system that can do the left and the right in there, but it's going to give me a z-score of 1.64. Uh, let's call it just 1.64. So I know that's equal to 1.64, and that would equal x minus 20 divided by 4. That's my z-score that I'm looking at. So I'm going to take to solve for x, I need to multiply both sides by 4. So take that answer and multiply it by 4. That gives me 6.57, and that's equal to x minus 7. So 6.57 equals x minus 20. And then to get x by itself, we need to add that 20 to both sides. And that'll give us 26.57 minutes. So the longest 5% of patients will take over 26 minutes, 26 and a half minutes for them to recover in there. So we've got two different commands there to work with. We have um, uh, we've got the normal CDF, and the normal CDF, you got to feed it two values. You have to feed it a lower bound and an upper bound, and it gives you the percentage of values, the probability, the percentage of your population that is between those two bounds. And then the inverse norm works the other direction. If we're started with the percentage, so we want to know the slowest 5%, the biggest 10%, something like that, we're going to use the inverse norm to find the z-score and then do some algebra from that z-score to find the actual value. Okay, so good luck on these. These take some practice. They get used to them. But we do use this normal distribution. Again, it's the usual distribution. We use it a lot, so you will see it a lot throughout this quarter.